Alright, another extreme graphing video. I'll do the usual stuff. First thing, let's work on the domain. You should know that the function just e to the x is defined for all real numbers. So if anything is going to cause us a problem here, it's what's in the exponent. And up here, since I have x squared in the denominator, x cannot equal 0. So my domain will be negative infinity to 0, union 0 to infinity. Range, I'll get that later on. Zeros, if you try to solve e to the negative 1 over x squared equals a 0, so if I'm working on the intercepts, I'll start with the x-intercepts. If you try to solve this equation, there is no solution. I'll just sort of remind you of the function e to the x for a second. It goes like this. And skyrockets up, crosses at 1. When x is equal to 0, it's equal to 1. But what happens is it's always above the x-axis forever. So whatever you plug in up here, e to that is going to be a positive number. So there are no x-intercepts. How about y-intercepts? Well, in order to have a y-intercept, I would have to allow x to be equal to 0, and that is specifically prohibited in this problem. So there's none. Already a very odd function indeed. No zeros, no y-intercepts. Well, let's go on with first derivative stuff then. Remember, the derivative of e to the x is e to the x, so I'm going to get this part, but then I have to multiply it by the derivative of negative 1 over x squared. Now, you can do the quotient rule and stuff like this, but let me, instead of that, let me change this in here to x to the negative 2. I think it's a lot easier to do the power rule than it is any other rules, to be honest with you. So I'll get e to the negative 1 over x squared times, now this negative 2 will come down and make that a positive 2, x to the negative 3. Now we usually set this equal to 0, so I will set e to the negative 1 over x squared. I'll put the 2 in front, I think, and I'll put the x cubed down here. Now, if that's to equal 0, I would have to multiply through by x cubed, and I would get 2e to the negative 1 over x squared equals 0. But I'm in the same situation I was at the beginning. There's no solution for this. E to anything is a positive number. So, there's no zeros. But there is a critical number at x equals 0 because the thing is undefined, the derivative is undefined when x equals 0. If this isn't enough to tell you, this certainly is enough to tell you. So when I draw my number line, I'll mark off 0, and once again, you know why I put that circle there to let you know that it's not defined. Let's go ahead and pick a negative number. I really don't care. I'll use negative 1. If I throw negative 1 in here, like I said, e to whatever is always a positive number. So whether this thing is positive or negative will be determined by the denominator. So when x is negative, x cubed is also negative. So this is negative, decreasing before 0. If I pick a number over here, say 1, plug it in, I'll get a positive number divided by 1, which will be positive, so it's increasing. Now 0, unfortunately, is not going to be a local minimum. However, there may be a hole in the graph, something along those lines, where the minimum would be there, but the hole will be in its place of where the minimum is. So I don't have a local minimum, but I do know that I am decreasing on negative infinity to 0, and I'm increasing on 0 to infinity. So as far as I can tell, no local extrema. So we'll move on to the second derivative. Let me grab, I like this version of the first derivative, so let me rewrite that. I have f prime of x equals 2x to the negative 3 e to the negative 1 over x squared. And I'm going to put a dot here because I'm going to use the product rule when I take the derivative. So f double prime, I'm going to do it really carefully here. Let's start with the derivative of this piece. You'll bring the negative 3 down and you'll get negative 6x to the negative 4. E to the negative 1 over x squared plus, now leave this part alone, 2x to the negative 3, but take the derivative of this. And this part is what we started with. So that portion will give us e to the negative 1 over x squared times, I believe that was 2x to the negative 3. Yes, it was, 2x to the negative 3. And let me simplify a little bit because I got to figure out where this thing is equal to 0 and stuff like that. So what I'm going to do is, well, you can factor out an e to the negative 1 over x squared, certainly. But you may not know, or you may not have had a lot of practice in factoring out x's with negative exponents. Let me go ahead and multiply the 2x to the negative 3 times 2x to the negative 3. Now, what you want to do when you're going to factor out is try to factor out the lowest power of x from everything. X to the negative 4 is not the lowest power. The lowest power is x to the negative 6. So I'm going to factor out negative 2 x to the negative 6. And I'm also going to factor out e to the negative 1 over x squared. What will be left? Well, from this part here, I will have positive 3x squared and from over here, I will have negative 2, and then we'll set this equal to 0. Now, as I've mentioned, there is a critical number when x is equal to 0. This is not defined when x is equal to 0. If I multiply through by it, this part here is not going to give me 0. So I'm not going to get a 0 from the 2x to the negative 6. I'm not going to get a 0 from e to the negative 1 over x squared. The only place I'm going to get a 0 is from 3x squared minus 2. But keep in mind, there is a critical number of x equals 0 here. So we'll set 3x squared minus 2 equal to 0. Or x squared equals 2/3. And then x equals plus and minus the square root of 2/3. I don't care if you try to rationalize the denominator or anything like that. It really does not matter to me at all. So my critical numbers for f double prime, they are 0. That's where it's undefined. Plus and minus the square root of 2/3. Put those on a number line. And once again, I'll put that little circle above the 0 indicating that that's not in the domain. The derivatives aren't defined there. got a spot for negative 2/3 to the left and a spot for positive 2/3 to the right of 0. Now, I don't know what exactly these numbers are equal to. This is like 0.67. Take the square root of 0.67. I don't know that off the top of my head. So, what do? Go to the calculator just to give me an idea of what this thing is. So I get about 0.8. So this will be negative 0.8, positive 0.8. So what I'll do then is let's throw in, well, this will be easy. Out here, I'll put a -1. And to the right of radical 2/3, I'll put a +1. In here, I guess I can do like 0.5, negative 0.5, and a positive 0.5. And let's see what we get. All right, I am going to take f double prime of x and rewrite it just a little bit to help myself out with the signs. That's a lot of stuff up there for me to try to figure out. So let me rewrite it down here. F double prime of x equals -2 e to the -1 over x squared times 3x squared minus 2 all over x to the 6th. The reason why I like this version of it is because no matter what, x to the 6th is a positive number. I can't plug in 0. E to the -1 over x squared is a positive number. So they have no bearing on what I'm going to get as far as signs are concerned. All I have to worry about is whatever the sign of this is, I'll take the opposite and that'll be the correct sign. So let's try the -1. If I throw -1 in, I'll get 3 minus 2, which is positive, but then the -2 will make this negative. So it's going down. Sorry, not down. That is like this, concave down. I'll put C, D. Now if I put in -0.5, oh, by the way, you should recognize symmetry. If I were to replace x with a -1, I would get exactly the same result. So likewise, I'm going to get the exact same result in here once I figure out which either of these is. So if I plug in 0.5, it'll be a little bit easier. If I plug in 0.5, 0.5 squared is 0.25. 3 times 0.25 is 0.75. 0.75 minus 2 is a negative number, times a -2 makes it positive. So we are concave up there. Similarly, I'll be concave up there. So let's go ahead and put a CU, and then a CD. And since we're defined at negative radical 2/3 and positive radical 2/3, we are changing concavity from negative to positive there. I'll have a point of inflection at negative radical 2/3, and I'll have a point of inflection at radical 2/3. Well, what will be the x value? I'm sorry, those are the x values. What will be the y value for each of those? So remember, f of x equals e to the -1 over x squared. By the way, this is an even function, which means if I plug the negative or positive version of radical 2/3 in, I'm going to get the same answer for either one of them. So we'll just do the positive one. F of the square root of 2/3 equals e to the -1 divided by the square root of 2/3. But that thing is squared. And I believe that will then be e to the -1 over 2/3, which equals e to the -3/2. So I have points of inflection. My points of inflection are plus and minus the square root of 2/3, comma, e to the -3/2. And we are concave up on negative radical 2/3 to 0, union 0 to radical 2/3. I'm not including this because the function is not defined for 0, so I'm not going to include 0 in that. So from negative radical 2/3 to 0, union 0 to the square root of 2/3. And it's concave down everywhere else. So it will be concave down from negative infinity to negative radical 2/3. Union radical 2/3 to infinity. So I've got, I think, what I need here. Let's go ahead and throw in a rough graph. Like usual, I'll check it with a computer-generated version. Let me write down the things that I have. All right, I couldn't plug in x equal to 0. However, I'm concave up here and here. I had points of inflection here. Let's see if I can, the square root of 2/3, remember we said it was about 0.8. So at these two, somewhere around 0.8, I'll just throw it in here. Let's do square root of 2/3, I'm just estimating, negative square root of 2/3. Now e to the negative 3/2, that can't be very big. Let's use the calculator to give me an idea of what that is. So I'll do second above the ln button, and I'll do negative 1.5. About 0.22, okay. So we might have something here. It's not going to be big. I'm estimating. Now, what happens at 0 or around 0? What happens in here? Well, you should know this. The limit. As x goes to 0 of negative 1 over x squared equals negative infinity. Because if you come to 0 from the left to the right, the square is going to make it positive, but this negative will make it negative. So, well then, what's that doing there? Well, if you have the limit as x goes to 0 of e to the negative 1 over x squared, you should remember that e to the x is a continuous function. That means that I can take and rewrite this as e to the limit as x goes to 0 of negative 1 over x squared. Well, if this is going to negative infinity, e to something that is super small like that is 0. I don't know if I covered that in an earlier lecture, but let me write this down here. I'll put a little note. I think we talked about, because the general graph, you knew that y equals 0 was a horizontal asymptote, and this graph tended to it as x went to negative infinity. So let me just cordon that off. So what happens here then is as x goes to 0, the function's going to 0. So we're going to have in here a hole, and then between negative radical 2/3 and 2/3, I believe we were concave up, which we were. So it's going to go like this. It's going to open upward, and then I'm going to hit this point, and it's going to be concave down after that. So we got this, the hole at 0, and then from then on it'll be concave down after that. Remember, it's an even function, so it should look the same on both sides. I'm going to see if I can even this one out a little bit and make it look a little better, or at least a little closer to the one on the right. So I'm guessing on something like this. Now, it is e to a negative number, so I should check for horizontal asymptotes. H, A. That's when we do the limit as x goes to infinity, e to the negative 1 over x squared. And because of the continuity of the e to the x function, I'm going to get e to the limit as x goes to infinity, negative 1 over x squared. That equals e to the 0, which equals 1. Throw in, since it's an even function, you're going to get the same thing if you throw in negative infinity. So I'm going to have a horizontal asymptote then of y equals 1. So I think I have everything I want as far as graph. There's going to be a hole in here. It's going to come down, concave down, concave down. Oh, I should have put e to the negative 3/2 there to indicate that that's the y value of these points of inflection. So my graph will be something like this, kind of rough, but I'll let the computer do the talking for me. Alright, here's a sketch of the graph. Let me go ahead and put in my points of inflection. They happened at negative radical 2 over 3. So I'm going to put it, I remember that was about 0.8, and this is 0.8, so I'm going to just try to get it right about there. Negative the square root of 2 over 3. So wherever that meets. And then I think I may be off because the y, e to the negative 3/2, if I can remember, what was that number? E to the negative 3/2 was 0.22. So it's got to be above there. So where I've drawn it is not accurate. Let's see. I can probably get the 0.22, roughly speaking. There's 0.22. So I'll put the dot here, which is really closer to the 0.8 that I sort of suggested. And it might be easier just to do this. Negative the square root of 2/3, comma e to the negative 3/2. That's a point of inflection. And then I have one, put it right at about 0.22, 0.8. So I get the square root of 2/3, comma e to the negative 3/2. That's another point of inflection. Notice there is no local maximum. This is interesting though. Look at what the computer is doing here. It makes it flat. It's because these numbers for the computer are so difficult, so compressed that it can't display them properly. That it's concave up according to the calculus. You know that this is concave up so that you know what the computer is trying to tell you here is a falseness. So what do we do about this then? Well, we do also, by the way, the graph is not showing us the hole, which I mentioned the calculator might be able to do. You need to put a hole here. That's something, let me put it in a let me put it where it really is at. You can see this is something the calculator did not pick up on. You had to do it for the calculator. So it has a hole at 0, 0. So what's the range? Well, it goes down as close to 0 as you can possibly get, but it doesn't actually get there. And it goes up to 1. Now, I know that it can't equal to 0. I've already talked to you about that. But how do I know it doesn't actually touch the horizontal asymptote? So, is it possible for e to the negative 1 over x squared to equal 1? Well, to solve an equation like this, you would take the natural logarithm of each side. The natural log of 1 is equal to 0. The natural log of e to the negative 1 over x squared is negative 1 over x squared. Now you know it's not going to have an answer because 1 over x squared is never equal to 0. But going through the motions, I'll multiply through by x squared. And that is a contradiction, so this is not possible. So our range is strictly 0 to 1, and I'm not including 0 or 1.